So, welcome everyone for afternoon session. The first talk this afternoon will be by Fabrizio del Monte about cluster integrable systems and five-dimensional BPS spectrum. Please.
Thank you for inviting me to this conference. In fact, last time I was at this conference, I was still a student here. So it's quite a nice moment after the pandemic to come back and to give a talk here. This is something that it's the idea of the program is to use discrete integrability to compute the full spectrum of stable states of five-dimensional quantum field theories, like the ones that Professor Cano described this morning. And this started towards the end of my PhD with Julian D'Alessandro, and then we kept studying this topic and making it a bit more precise with Pietro in the past couple of years. And I will talk about also a paper that just came out a few weeks ago, just by myself, in which some things are put a bit more into perspective in the terms of special solutions of this integrable system. The story is that of a connection that is being built between various topics of quantum field theory and string theory, and various topics in mathematical physics, geometry, and integrable systems. And really, there's a lot of ideas on both sides, and there's been formulas from gauge theories have provided new solutions of integrable systems, but then you're able to compute new quantities. There's a beautiful story about non-perturbative partition functions that relates to these integrable systems. But today I will focus just on a few aspects of these connections that involves the BPS spectra, and in particular five-dimensional quantum field theories on one side. And on the other side, I will touch on some certain TBA equations that arises from the geometry of the moduli spaces of these theories. If you're a bit familiar with the work on Gayottomo and Naiske, that's where it comes from. And on the other side, you have Q-Panleve equations, so discrete integrable systems, and WKB approximation, but for Q difference equations. And the general picture and the general physical motivation behind studying, one might ask, why five-dimensional theories? Why should I care? Well, the thing is that if you compactify type 2A string theory on a Calabi-Yau threefold, well, then it's well known that you will typically find a four-dimensional n equals to 2 theory on the four-dimensional space. So you have this compact six-dimensional space, type 2A is 10-dimensional, and you go down to 4D. But actually, that is not the full story, because if you're doing type 2A, you should always keep in mind that there's this hidden M-theory circle. So there is an 11th dimension going on. And then the BPS states, the non-perturbative physics of these theories is actually that of a five-dimensional theory with, if you think of it as coming from string theory and then M-theory rather than just the quantum field theory, which is of course fine by itself. Then you have this hidden circle, and you should study a five-dimensional quantum field theory on R4 times S1, and this S1 is the M-theory circle. And then if you think of it in terms of type 2A, and you want to study the BPS states, well, in particular, I want to study the BPS particle states. I want to find what BPS particle states are stable. And because there are also some BPS states in these theories which are not particles, and I will not touch on them. So what are BPS particles in the type 2A description? Well, they're deep branes that are wrapping some holomorphic compact cycle on the compact, well, not compact, on the Calabi-Yau threefold. And you can think about it this way. If you have some, let's say some D2 brane, this is a three-dimensional object, two space, one time, then it's wrapping some on the Calabi-Yau threefold some compact cycle, and then there's one time direction which is free, and effectively the five-dimensional theory just sees a particle, even though it's coming from a deep brane. And so you have D0 brane on 0 cycle, D2 branes on 2 cycles, and D4 branes on 4 cycles. And those are your BPS particles. Yes, please. So these are so the compact support. So the BPS charges are the homology cycles with compact support.
H to upper compact is equal to H-Law 4.
Okay, yeah.
So it's a decobrain wrapping this H2. I mean, any.
Right, no, but so the thing is here, because it's just general picture. So here, this is cohomology. So I'm thinking about the fact that actually the D brain wrapping on this compact cycle gives rise to some coherent sheaf, so some localized vector bundle on these D2 brains, and that is the meaning of that formula. But since you're taking compact support, it's just even cohomology, you can kind of switch between the two. Now, the main idea is that if we want to talk about supersymmetric sector of these theories, then you can rephrase questions just in terms of a discrete integrable system. And this is much nicer because you get some difference equation for some finite dimensional classical mechanical system. So you're starting from some strongly coupled QFT in 5D with an effective gauge theory description, and then you write things in terms of some classical mechanical question, for which you can write exact solutions. And the type of discrete integrable system that I will describe are so-called cluster integrable system. In particular, if you just focus on the simplest examples, which are 5D SU2 gauge theories at low energy, well, there's a classification. So these have rank 1 Coulomb branch. And there's a classification of these theories, which was done by Seiberg in the 90s. And it coincides with the classification of Q-Pan-Levé equations. So these are 5-dimensional rank 1 superconformal field theories that at low energy are gauge theories. And this is the same as the classification of Q-Pan-Levé equations by Sakai in the early 2000s. And you get these affine root lattices. These affine root lattices are just the lattices of flavor charges of the quantum field theory. And they become the lattices that describe the symmetries or the time evolution of these discrete integrable systems. And in particular, I will focus on what are called algebraic solutions of the cluster integrable system, that they're very special solutions that are invariant under some involutions of these affine root lattices. So what can we, and of course, these theories have been studied through a lot of different approaches, Q-deform CFT, quantum curves, cluster integrable systems. Of course, you can also do a fully, like Professor Kano this morning, starting just from instanton counting. These are more the approaches related to string theory, at least these two. And I will focus on the one through cluster integrable systems that were introduced for Q-Pan-Levé equations by Bernstein, Gavrilenko, and Marshakov a few years ago. So what can we extract from discrete integrability? Well, it turns out that we can say quite a lot just from this discrete system. First, we can find appropriate chambers in the moduli space of these theories where you can compute the full spectrum of stable states. So this is a highly non-trivial statement. You have a 5-dimensional gauge theory in low energy. It flows to some strongly coupled point in the UV. And you're saying that you can describe all the stable state for this theory in a regional moduli space. But you can actually do more, because once you compute the spectrum of states in this region, you can compute what is called the Kontsevich-Soibelman invariant or quantum monodromy. And this quantity is invariant as you move around the moduli space of the theory. So from the spectrum in this region that now you know, you would be able to, in principle, to compute the spectrum in all the other chambers of the theory. Of course, it might be computationally intensive, but this would give you the answer. And then we also have a relation to these TBA equations that describe some good coordinates on the Coulomb branch of these theories. These are flat coordinates for the hyperkähler structure on the moduli space of these theories. And the description in terms of WKB quantum periods for a corresponding difference equation. This comes from a quantum curve in the mirror symmetry context. And of course, you also saw part of it this morning. This I will not do much. I will not discuss much about this point. But the solutions of these systems, they can be written explicitly. The general solution, they can be written explicitly in terms of Nekrasov partition functions. So essentially, you have this class of, from this point of view, they're a class of special functions. You can write everything kind of explicitly, and then you answer questions from this. So this is kind of the overarching view. And what I'm going to discuss, I'm going to first recap some more details about five-dimensional BPS states a bit more precisely, and the tools that we use to describe them. And then I will show you the example of these rank 1 theories, which are five-dimensional SU2 superior males with matter at low energy. If there is time, I will also show you, so this nice chamber typically corresponds to exactly these gauge theory phases of these five-dimensional superconformal field theories. If I have time, I will also discuss how to extract some information directly about other chambers in which you have wild spectrum, which means arbitrary states of arbitrarily high spin. They're organized in some crazy way, but you can still make some. You can still derive some things, not as much detail as the gauge theory phases, but you can study it. And then I'll conclude with some comments about the connection to QWKB approximation. So, I mean, for now it was just the general overview, but if there are any questions at this point. Okay. So, as I said, we have this lattice of charges. So you label every BPS state by its quantum numbers. And these quantum numbers, you should think of exactly what I was saying before. On the D brane, you have a gauge field, and mathematically, it's what is called a compactly supported coherent sheaf, because to make sense of essentially vector bundle localized at some subspaces of manifolds. And so the cohomology of the Calabi-Yau gives you the electromagnetic charges and the flavor charges of these states. They're the quantum numbers of this state. And of course, these are just its charges. And to fully describe the state, you will need its mass and its spin. Like what type of particle are we talking about? And for that, you need a central charge. As you well know, these are BPS states. So their mass is given by the BPS bound. So you have the central charge that you can view as a linear function from this lattice to C. And the modulus of this function is the mass of the BPS state. And then if you go at low energy, the BPS states are the lightest charged particles that you can have. So if you go at low energy, you can describe them through a low energy effective supersymmetric quantum mechanics. And the phase of the central charge is essentially the Fayet-Iliopoulos coupling of this low energy quantum mechanics. So here we're missing just the spin, and this is encoded in what is called a protected spin character. This is an index that you can compute from this supersymmetric quantum mechanics if you want. And in mathematics is known as the Motivic Donaldson-Thomas invariant. So we will not need it in full generality, but just for concreteness, for a hypermultiplet, you have omega equals to 1. For a vector multiplet, so this is hyper. And for a vector multiplet, this is y plus y inverse. So just this you can think of some characters, but let's not go too much into that. And then finally, the last quantity is the Dirac pairing, because I said that these give you the electric and magnetic charges, and then if between electric and magnetic charges you have a Dirac pairing, and if it's non-zero, it means that the two particles are mutually non-local, so they cannot be in the same Lagrangian description. And these typically you have monopoles, dions, everything. And this Dirac pairing geometrically is the Euler pairing of these sheaves that live on this compactly supported sheaves. And you can write it in terms of these churn classes of the sheaf, its dual, and the these spaces, just to be a bit more precise, these spaces that I'm considering are non-compact Calabi-Yau triple. So you only have gauge theories. You're not considering gravity or whatever. You just have a gauge theory description. And then you have the Calabi-Yau triple is the total space of the canonical bundle over a surface S. So in this Euler pairing, it appears the churn character of this sheaf that's coming from the D brane, and then the Todd class. It's another characteristic class of this surface S. So why do I'm stressing so much about the Dirac pairing? Well, because it actually is the main thing that I will use. Because from the Dirac pairing, you see, this is the antisymmetrized pairing. So if you choose a basis of BPS states, fundamental states, then essentially you can represent it as an antisymmetric matrix. So, and an antisymmetric matrix, you can also represent it as a quiver. So, just to be a bit more concrete, the idea is the following. You have this central charge. So you have all your BPS states. Every state will have a central charge. But because of CPT symmetry, the CPT symmetry maps the central charge to minus the central charge. So essentially, you can focus just on a half plane of central charges. And then, because then all the other central charges will just be the CPT conjugate, the antiparticles of this half plane. And then, if you, in this upper half plane, you fix a basis of BPS states, these are your fundamental states, and all the other states are given by some linear combination of these vectors of charges. And then you write this Dirac pairing in this basis of states. It is an antisymmetric matrix, and you represent it in this way. So if you have two, if the matrix has a 2, then you have 2 outgoing arrows. Minus 2 is 2 incoming arrows from the respective nodes. So this, for example, is the quiver that would correspond to local P1 times P1 or 5-dimensional pure SU2 super units. And why do we like a description in terms of quiver? And who are the states sitting in the vertices? So the states sitting in the vertices, they are some, you have to pick a good basis of what is called simple objects from this categorical point of view. But essentially, you can write them as you fix, you study the churn characters of the sheaves that can live on this.
Just in this example, you said that you have some lattice of something unbelievably complicated. Yeah? Mm-hmm. You have 5-dimensional field.
Yeah.
In contrast to 4 dimensions, for example, monopoles are not particles.
Yeah.
I do not understand. Do you exclude them or not?
No. I mean, you can. Because
in the beginning, it seemed to me that you said that
but the monopole would be a particle because the monopole would be the D4 brane, right? The D4 brane wrapped around the 4 cycle, it would be an elementary magnetic charge.
Monopole is a particle in 4D, yeah?
Yes.
In 5D, you should get some extra dimension.
Right, but what I'm saying. Yeah. I mean, so the point of view is that these are actually, because of the S1, you can think of them as 4-dimensional theories with an infinite number of fields.
So
they're 4-dimensional.
Everything in infrared, yeah? Where your radius is very small. So you are on far distances.
I mean, not. No.
So the D4 leads to an M5, it wraps the circle.
Yeah.
And the word line in R4. So it looks like a particle.
So basically, in simple terms, the circle is shrinking. Yeah. Okay.
No, the circle will be kept fine.
Yeah.
Fine. But there will be a particle string.
Yeah.
I'm sorry, I was, of course, I'm asking you the same stupid question.
Right, but. Yeah.
There fractional grain, I think it's possible to explain it.
At least in other case makes sense. In other cases, it's more electrified.
Yeah. I mean, yeah. But yeah, it's a particle from the point of view of this four-dimensional Kaluza-Klein theory.
Yeah, right? It's of course, no question.
But once you write everything geometrically in terms of these sheaves wrapping compact cycles, then you kind of forget about it, and you don't need to have the radius small anymore. That's kind of giving you some semi-classical intuition.
So another maybe good time for these two questions. So an instanton, is it like is it state in this sphere that for in 5-dimensional theory? I mean, is it particle, instanton particle, is it taken into account?
Yeah, I would say that the instanton, yeah, the instanton are part of what I'm gonna call the flavor lattice, because you know, the instantons are particles in 5D and they have a conserved current, the instanton current. So, and it is a flavor, it is a global symmetry, topological global symmetry of the theory. So it is part of the description, and it's actually, for example, if you know that example, you have this A1 affine, and the A1 is exactly the instanton.
Sorry. So you said that you are focusing on people that are total space logical boundary
Yeah.
compact surface.
Mm-hmm.
What is this crucial? Because I mean, now you're using BPS techniques. I guess you can also connect other things.
Yes, you can, but just for concreteness, I'm focusing on this, and it might be that yeah, I don't have a good notion of how it would generalize to. So this. I mean, yeah, but the conifold, you will see that I use heavily in this computation. I use heavily wall crossing, and in the conifold there's no wall crossing. So the conifold is kind of a bit of a, from the point of view of this integrable system, is an example that's a bit too trivial. You need the existence of a D4 brane that's there. Other, yeah.
So is basis is it unique in some sense?
No, it's not unique, and the ambiguity is exactly that. If you well, maybe you can ask me that question in a few slides because I think I'm going to answer it in the next slide. So the non-uniqueness comes into the choice of the upper half plane, essentially. Just the short answer is that. So how is it that starting from just this quiver and this lattice of charges, we can compute the BPS spectrum of the theory? Well, this is a method that was developed for four-dimensional theories by Ceccotti and Baffa, and we generalize it for five-dimensional theories where it's a bit more subtle, but it's called the mutation method. And just to give you an example of how it works, I will consider the weakly coupled chamber of pure SU2 super Yang-Mills in 4D. So this is a usual Seiberg-Witten theory, and the corresponding quiver is this one. You have only two nodes, and they correspond to two elementary states. One is the monopole and one is the dione. Monopole and dione. And weakly coupled. But the two nodes are the monopole and dione.
Why not W boson?
Because the W boson is not cannot only hypermultiplets can appear as nodes of the quiver. So these nodes of the quiver are not necessarily, they are part of the spectrum, but they're not the spectrum. So here you have this basis of states constituted by the monopole and the dione, and here you could have any. I'm just drawing the central charges in the complex plane, and this is my choice of upper half plane. But you see, the choice of upper half plane is kind of arbitrary. So what I can do is that I can start rotating this upper half plane. And then what happens is that exactly you will have a new basis, because the basis is constituted by the central charges that are closest to your choice of upper half plane. So if I rotate, I will start having a new basis, and then I will discover, and the new basis is constructed by this rule that just uses this B, which is the matrix encoded in the quiver. And this is called the mutation rule. And also the matrix changes. Actually, here I didn't update the picture. It would just flip these two arrows in this case. So you start rotating and you say, so actually, in this case, you do the mutation rule and you start seeing that you have some new bases constituted by these two new states. So these two states, you did nothing physically. So these two states were already in the spectrum. It's that you just start seeing them when you perform this operation. And it's purely combinatorial. So you can continue doing that. And doing that from the other side, it's just a different rule of mutation. Here you would have a minus. If you do it clockwise or anti-clockwise, it just changes the sign of.
So how? So we make mutation in first or second vertex.
Right. Sorry. So you mutate on the vertex that is going away. So here you mutate on gamma 1. And then here, actually, this would become the second node. So you would mutate at gamma 2, and so on. You have to keep track of what charges are in the nodes in the process.
So really we have only two cases of quivers, but so
yeah, the only two things that you can do here is you can have either gamma 1 here and gamma 2 here, or you can have the opposite orientation. And this is strongly coupled chamber, weakly coupled chamber. And if you did a strongly coupled chamber, you could just find just your usual strongly coupled states, and you wouldn't find all this structure. But in the weakly coupled chamber, you find these towers of states, which are the towers of dions, and the limiting rays of dions are vector multiplets. As I said, vector multiplets never appear as nodes of the quiver, but they appear as limiting rays. So this is kind of the full picture of the this is the picture of the spectrum that you would get. You see, you get all these towers of central charges, and you get this limiting ray, which is just gamma 1 plus gamma 2, which is the vector that they're limiting to.
So the statement is that from the basis by the mutations, we obtain all the states.
You obtain all the states outside of the limiting ray. So in this, because you don't see this after a finite number of mutation. You see this as a limit of infinite number of mutation. So in this case, there's not much you can say. There's gamma 1 plus gamma 2, but we will see that there can be more complicated structure on the limiting rays, especially the 5D case, and then you will need some more attention. So this is kind of what happens for 4D theories, and this is kind of in 4D theories. The simple chambers that you can find are finite chambers, like the strongly coupled chamber of pure SU2 superior Mills. You have a finite number of states, and they're strongly coupled. In weakly coupled chamber, you have a vector multiplet, and you have an infinite number of states, and they're dions that are accumulating on these vector multiplets. Now, in 5D, finding such chambers is much harder, actually. Until recently, people were not even sure that they existed just from this description, just tame chamber, in which you only have hypermultiplets and vector multiplets. And the idea is that we want to find consistent methods to find these nice chambers in 5D. And you will not find finite chambers in 5D, at least. You don't expect to find them, because this is you have a theory in R4 times S1. So you always expect to have at least towers of Kaluza-Klein modes that are roaming around. So the spectrum will typically be infinite. So yes, this is what I did now, what I said now in words. And so this is kind of the types of chambers that you can have, what I was saying now. Like finite chambers, these are not here in 5D. Then you can have tame chambers, so you have vector multiplets and hypermultiplets, but typically you will find wild chambers. Now, wild chambers work a bit differently in the sense that, you see, you were able to do this sequence of mutation, and then you would sweep out the whole upper half plane because you would just exclude this limiting ray. But let's say that you have two limiting rays and they're distinct. Then within this cone, you will never be able to reach by mutation, because if you do an infinite number of mutations on one side, you get to one limiting ray. Infinite number of mutations on the other side, you get to the other limiting ray. And then what people observed is that in this cone, there are central charges of states of higher spin that are organized as they're called wild cones, in which you have higher spins organized in Regge trajectories. And we want to avoid that. So we call these five-dimensional chambers, which would be the analogs of tame chambers, we call them with Pietro collimation chambers, because we want to collimate all the states like a light ray collimated on the central charge of the D0 brane. You know that you will have D0 branes are the Kaluza-Klein modes, and you know that you will always have towers of these D0 branes, and we want that to be the only accumulation ray. So that's the main idea. So how to find these chambers? This is where these cluster integrable systems come to aid us. So just to quickly, very lightning review of what we mean by cluster integrable system is that you have what are called X-cluster variables. You have their maps. The central charge was a map, linear map from gamma to C. These are birational maps from gamma to C star. And this was the Dirac pairing. So the Poisson bracket was this antisymmetric matrix. So if you just write it in the basis of the quiver, this will be just the Poisson bracket between two nodes is the number of arrows with sign between the two nodes. That's it. And the flavor charges are the Casimirs of the cluster integrable system. So flavor charges physically, they have no electric or magnetic charge. So the Dirac pairing will be zero with everything. From the point of view of integrable system, the Casimirs have zero Poisson bracket with everything. So these will be the X variables corresponding to these flavor charges. And then these mutations that I was doing before on the gammas descend to these X cluster variables as Poisson maps, and they act in this birational way on the X cluster variables. The time evolution on this system, you have time evolutions that are some discrete flows, so that you write as sequences of mutations and permutation that leave the quiver invariant. So from the point of view of the root lattice, they're just translations. You're shifting the affine roots of this affine root lattice that was the flavor charge lattice of the 5D theory. You shift them by units of the D0 brane charge. And the X cluster variable corresponding to the D0 brane charge we denote by Q. Since mutation, you can see them as some cyber dualities of these 5D theories. If you think about it from the point of view, from a physical point of view, these sequences of mutations, they were also called in the literature duality cascades. They're self-dualities of the theories that have this kind of infinite they're not periodic. You can iterate them and you get some infinite translation.
Mm-hmm. But can those mutations from four-dimensional stuff as well be interpreted as safer biologists?
I'm not sure. I don't know.
But those safer biologists in 5D, which you mentioned here, are they the same, like, at least like conceptually the same as safer biologists in 4D and response?
I mean, I would say I would say that I mean, this is, so you see, what you're doing is, in the perspective that like from the point of view that I was saying before, you're you had this low energy, effective supersymmetric quantum mechanics, and it was described in terms of this basis of states, and then you stay within the same theory, but now you're changing the quiver, you're changing the basis of states, so you have a different infrared description, but it's from the same UV theory. So yeah, actually I would say that it's kind of they also contain that, because in some cases they can be then twists, but
maybe you can explain in this example, this quiver, yeah, if
yeah.
you make a mutation, you know how it transforms.
Yeah.
What is this 5D dual theory corresponding to the transformed quiver?
I mean,
I'm still afraid to ask what is the original, maybe a stable dual.
No, but this is it's really just if you write down the super. I mean, it would take quite a while, because you have to write down the supersymmetric quantum mechanics starting from the quiver, and then now you have to mutate. You know how the quiver transform, but I mean, it would really bring us far away from from
no, just the answer, not of course writing everything down, but what will be the you say that this is some duality transformation in 5D, yeah?
Yeah.
What is the result in dual theory?
It's
what do you say? It's a 1D duality, no?
yeah, it's in 5D in the sense that you still have the same 5D theory, but in the infrared you have a different effective description in terms of the supersymmetric quantum mechanics.
That is a description of the war line of the BPS particle. The 5D theory is fixed and once and for all. It's just a different. It's a 1D Seber duality of the quantum mechanics that is part of the BPS war line.
Yeah. Yes. Well. Yes, but that's exactly what the cyber duality is, right? You have a different infrared effective description of the same UV theory. No, it's not. It's not exactly like cyber dualities in 4D. I would say that it's just. I mean, people use this term, but I don't think it's exactly the same as the original cyber duality.
And is there any difference in your picture between the theories with relatively small amount of multiples, like this one, which has a number of square units, and the theories 5-dimensional, which do not have many but still correspond to the Zyber picture and to the
yeah.
Is there any difference in the description between these two cases?
I will show a theorem from the last paper that requires a certain symmetry of the quiver, and well, maybe I can come back to this question just a bit further in the talk, because I think it will be answered just in a while. So, okay. So you have this discrete system with discrete time evolution that shifts these flavor charges by the zero brane. And the kind of thing that we want to solve with these cluster variables are these TBA equations. And these TBA equations arise if you compactify. So how did these are the Gayotto-Mornaytsky TBA equation. And essentially this Y gamma, I just try to distinguish. In the end, they will be cluster variables, but I would like, at least for now, to use Y gamma for the particular cluster variable that is solving the TBA equation. X gamma will be just some cluster variable in general. So these arise if you compactify further the theory on a circle. So in the class S, originally it was in this class S description. So you have 4D n equals to 2 theory. You compactify it on S1, you get a 3D n equals to 4 theory. And you get the line operators, the infrared line operators of these theories satisfy these TBA equations. Or, well, these essentially are just good coordinates on the moduli space of this 3D theory. In our case, you already have a theory on a circle. You would further compactify it on T2 instead of S1. You go from 5D to 3D, but still thinking of it as a 4D Kaluza-Klein theory, you would still have the same TBA equation for these quantities Y gamma. So these TBA equations then were formalized into what is called the BPS Riemann-Hilbert problem by Tom Bridgeland, which is just some abstract mathematical reformulation of this. And it is supposed to encode kind of all the geometry behind the BPS spectrum of these theories in kind of a more abstract construction. And then this was kind of an idea, but then it was shown that these two constructions are equivalent, the abstract one and the concrete one in terms of TBA equations by Alexandrov, Manshot, Persson, and Piolin, and where they really showed that these log y, these epsilon corrections are the worldsheet instanton correction to the central charges in these theories. So now let me explain the various things that enter in this equation. So this you can think of it as solving iteratively in this epsilon parameter, so kind of as an asymptotic series in epsilon. And this sum here, gamma prime greater than 0, means that you're summing over all states in your upper half plane. So this means that just to write down this TBA, you must already know the BPS spectrum of the theory. So that's kind of a prerequisite. Then you have this, which is a Dirac pairing. The integral here is on the ray in the plane of, complex plane of central charges, the ray where you have the phase of the central charge of this state. So it's an infinite semi-line that goes along the phase of that central charge. And then this sigma can be plus or minus 1. It's plus 1 for a, no, sorry, it's minus 1 for a hypermultiplet and plus 1 for a vector multiplet. And then, yeah, depends on the state. It can be plus or minus 1, but we will only need it essentially for hypermultiplets. And one thing that we can immediately notice is that if you have a charge gamma corresponding to a flavor charge, then there's no epsilon correction. So flavor charges do not receive this epsilon. You should think of it as G string essentially, and they do not receive correction in this epsilon.
Epsilon is a radius of the reduction to 3D.
Yes, it's I think it should be the radius. No, yeah, you can. Yeah. It's a radius to 3D. Yeah.
One of them.
Yes. Then no, epsilon is its radius. Yeah. So it's yeah. So if you think of actually, it will be more like radius times G string if you think of it in terms of worldsheet instantons. I think. But yeah, it's radius times the twistorial parameter from the hyperkähler moduli space point of view. Right. So the main content of this TBA equation is that, so what happens if you start varying the phase of this epsilon, right? If you vary the phase of this epsilon, at some point, you will cross the integration here, will pick up a pole. This will become singular because it will cross the integration contour. So then the discontinuity, when you start varying this phase, picks up this. This is called Kontsevich-Soibelman transformation. But you see that if sigma, if you're crossing a hypermultiplet ray, omega is equal to 1, sigma is equal to minus 1. This is just the mutation rule from before. So the discontinuity when you cross a hypermultiplet ray is just the mutation rule of the cluster integrable system. But well, so as I said, this is kind of a more complex problem than just finding the BPS spectrum, because just to write down the equation, this is a set of integral equations, and in fact, if you have an infinite spectrum, it's an infinite set of integral equations, and just to write them down, you need to know the BPS spectrum. But we can actually kill the two birds with one stone in favorable situations, because you can prove that if you have so you can kind of use it as an assumption that there is a permutation pi that is a symmetry of the quiver and of the BPS spectrum, and then work backwards and check consistency with this assumption. So if you have this permutation pi, a cyclic permutation of the quiver, so in that case, it would be either a Z4 that permutes these 4 nodes, or a Z2 that permutes 1 and 3 and 2 and 4. So if you have a permutation symmetry on of the quiver, and for which the sum of all the orbits of this permutation symmetry are flavor charges, then if you pick this configuration of a central charge, which in mathematical terms is called a stability condition, if you start with this initial condition on the TBA equation, then actually the solution to the TBA equation receives no correction in epsilon. In this point, it's just purely semi-classical. If you want, the quantum periods are the classical periods. And if you look at what this means from the point of view of the cluster integrable system, this corresponds to having some involution under which your system is invariant. And, well, this signals that you're considering an algebraic solution of the cluster integrable system. That for Köppen-Levé equations, they were discussed very recently by Bernstein and Shechkin in terms of so-called foldings of Köppen-Levé equation. But essentially, you have a classification of these foldings, and some of them will correspond to physical solutions, some of them not. Because this is kind of just saying, okay, I pick this, and if I do this, then I will not receive quantum correction. You have kind of pairwise cancellations in your TBA. But actually, there's a bit of a caveat. Well, no, there's a bit of a caveat because if from the physical point of view, if you have two central charges that are aligned, and these states are mutually non-local, so they have a non-zero Dirac pairing, then you're on what is called a wall of marginal stability. So if you think of two states, on some side they form a bound states, on the other side of this wall, they're not, the bound state is not stable anymore, it decays into these two states. But then if the central charges are aligned, you don't really know what is the bound state, what is the fundamental states. So you must be careful that the central charges that you're aligning are not mutually, they are mutually local, because then you don't have this issue. So for example, here, if I put on top of it, if I use the Z4, I put on top of each other all the central charges, then it's not physical. And also it's not particularly interesting. But if I put these two on top of each other, gamma 1 is equal to gamma 3 and gamma 2 is equal to gamma 4, then that I can. It's a Z2 involution. This theorem applies, and you find a very simple solution of the cluster integrable system. And before going forward, I want to mention that this theorem just uses a quiver and a symmetry. I've been talking about 5-dimensional theories, but as we were mentioning before, these quivers appear also in the context of 4-dimensional theories. So one example is the A1D4 Argyres-Douglas theory. It appears at a special point in the moduli space of NF equals to 3 super Yang-Mills SU2 in 4D. And you can, in some class, its quiver is just a square with one arrow between every node. So actually the same thing that I just said for this quiver, you can do for that quiver. And it will give an exact solution of this TBA for that Argyres-Douglas theory. And of course, the spectrum is finite. It's just a simple superconformal field theory in that case, but you can check that it's invariant under this involution. So it's fine. That I don't know. That I don't know. Yeah. Yeah. It's invariant under the involution. That's all I can say. I didn't compute the central charges. It's just a remark that if you want to try to, like, if someone wants to apply this theorem and see so that's the thing. Here, you're kind of treating the central charges. Let me explain this issue. You're treating the central charges as some kind of independent variables. But in general, the central charges will be periods of your Seiberg-Witten differential. So this solution will exist. It will have some geometrical meaning, and then you should check whether or not it's physically realized in the Cyber-Witten theory. So for example, for 5D SU2 superior mills corresponding to that quiver, we checked that it is realized. And in general, we think it will, and it corresponds to what is called the orbifold point of this local Calabi-Yau. You can reasonably think that it's related to an orbifold because I'm imposing essentially invariance under a Zn. So, but then you can deform away from this and you go from the algebraic solution to a more general solution.
Like, what you need is to have an actual reserve R symmetry on the Coulomb branch. So even if there is a series, those are the residuals that are symmetries to the check out the delta Martin.
Yeah, maybe.
And in 5D, we actually take I will talk about system.
Okay, that's great.
Also, it's accidental that are symmetry in all those cases that you consider.
Okay, perfect. Well, then we should discuss about it more. Let me just, okay, I have to be very quick because now it's being a bit late. So I just want to, okay, this is the example of the quiver that arises for 5D SU2 superior mills with an F equals to 4. In this case, you have kind of similar symmetry as the one that I discussed there. You can permute these two, and the same for the bigger square. You should just look at this quiver as two squares, one big and one small, one inside each other, and you just apply the same reasoning that I did before. And this corresponds to this involution of the linking diagram of d5 affine, that is the flavor symmetry. So, okay, then you just take this algebraic solution by imposing invariance under this. And then in terms of the central charges, the algebraic solution is just this. And this is what would be in terms of usual Cupan-Levé variables. This would correspond to Cupan-Levé 6. So this is the algebraic solution for Cupan-Levé 6 that corresponds to this chamber. And then you can, this is the BPS spectrum of the theory in terms of this basis of states. You have towers of, so you would have here these infinite towers of hypermultiplets here. And here on the real line, you would have some other hypermultiplets, the two vector multiplets, and towers of the zero branes, so Kaluza-Klein modes over the vector multiplets and hypermultiplets. So everything is in here. And you can see that the spectrum that you get from this collimation chamber, this we computed with Pietro a few years ago. And this kind of reasoning with the algebraic solution of integrable system tells you how to go in general about finding these nice chambers.
What do you call by algebraic solution?
Well, algebraic solution, if you think about it in terms of, so this would be the coefficient of the equation, and it's just, well, okay. One short answer is algebraic solution is the one invariant under the Dynkin diagram automorphism. And then you can see that it's just really some monomials in this case, it's just really some monomials in the coefficients. So that's, even in usual Paul-Levé case, so if for this quiver, you would have, so the condition would be x1 equals to x3, right? And you have x1 x times x3 is equal to t, which was the instanton counting in Nekrasov. So it's just, and then the product of all the x's is this q, which is a d0 brane. So x1 is t to the 1/2, and yeah, but
it's just equal to Casimir.
Yeah.
Some Casimir function.
Yes. And also in this case, you see, these A's are all Casimir functions. So algebraic solutions are just Casimir functions. They do not have Coulomb moduli. But the thing is that from, if you start from this point, and you can check for 5D SU2 superior mills that you get it from the mirror curve.
If you take local P2, you have this Z3 symmetry and no Casimir function.
Well, the only Casimir function is Q, right? So the algebraic solution would be just all the cluster variables are q to the 1/3. But that is on a wall of marginal stability for the reasons that I was saying before. Right, and then if you go a bit away from this, so if you deform from this region, but still staying within the same chamber in the moduli space, you will go from this super simple solution to the solutions that were shown this morning in terms of Nekrasov partition function. So you get that these x are ratios of Nekrasov, of dual Nekrasov partition functions, and you get kind of explicit formulas for the solution of these. And there is an intermediate situation, because of course these dual partition functions are very complicated. But there is an intermediate situation, which is that of rational solution. So actually, if you start from this trivial solution to the TBA, you can construct, by using these flavor symmetries of the theory, you can construct an infinite number of solutions of the theories, which are actually way more complicated. So this, here we had the D5 affine, right? So I start from this solution and I apply, so in D5 affine, I have different directions in which I can translate on this root lattice. So one is I said, okay, this is the time evolution and this is the algebraic solution for this time evolution. The other directions are symmetries of the theory. So if I apply another translation, which is, well, this complicated sequence of mutation, to the original algebraic solution, if I apply this other translation, then what I find is that you start from this, and remember these A's are just e to the some central charge over epsilon. So now you find a new solution, which is rational. This was algebraic. This is rational for obvious reasons. And but now if you think of it in terms of a series expansion in H bar, if you like to think of it in terms of trans series, this was just transmonomials. It's e to the something over H bar, over epsilon in this case. And this is the intermediate, the full solution that was in the general chamber was fully transcendental. You had an infinite number of transmonomials with a full perturbative saddle around. And this is the ones that you obtain by doing this so-called Beckton transformations on the algebraic solutions are just trans series with an infinite number of trans series term, because then you have to expand this denominator, but you don't have any perturbative series around the saddles. So this is interpretation if you like to think about in terms of trans series. And well, if you start from this,
sorry, but these are periods just of the flavor charges.
Yes. So in this, so this algebraic and rational solutions, everything is written in terms of the flavor charges. But within this collimation chamber, if you go away from this very symmetric point, and this is not in the original chamber. It's another chamber, but it's still a collimation chamber. And if you go deform away from that, you will find again.
How you deform away? By using
so no, you would think of it. So that's kind of open question about. So you deform away by just, for example, here I would translate these. So here, let's say that the next state is here. I move a central charge used as initial condition of the TBA just a bit like this, but without anything crossing. So, and I can do it, I can add another 4 independent parameters this way, and then you can do a matching of what is here and what are the parameters that appear in Nekrasov partition functions, and after you properly match the two descriptions, you get the expression in terms of Nekrasov partition function in these terms. But of course, you don't know if this new, you should check that, well, and it's a complicated question, at least for me. Maybe there's an easy answer to that, but whether or not this new configuration is just some, what is called a formal stability condition, it's just a configuration of central charge that is not realized as periods on the Seiberg-Witten curve. It might be realized if you add some surface operator, maybe. But or if you can also obtain these deformed ones in the Seiberg-Witten curve. Yeah, since I'm out of time, I just want to quickly mention that if you start from this NF equals to 4 case, of course, you can start decoupling hypermultiplets. And in the geometry, it means that you're shrinking some cycles. And with Pietro, when we tried to approach the problem just of computing BPS spectra directly, we were not able to cover the case NF equals to 3 and NF equals to 1 and NF equals to 0 with Chern-Simons term. And the reason from this new point of view is that, well, there are no algebraic solutions in this case. You can just check. There's not this involution that would correspond to a physical point in modular space in the sense that it's not on a wall of marginal stability. But what you can do now is you start from your NF equals to 4, you decouple, you find the BPS spectrum. So you have a full BPS spectrum and a new configuration of central charges. And then you can also check that if it's not symmetric, so it will not have this super simple solution to the TBA, but you can check that the BPS spectrum that you compute from the mutation method coincides with the one that you obtained by this decoupling procedure as a consistency check. So you find these chambers also in the cases where you don't have this symmetry. You do find the full BPS spectrum, but the solutions to these TBAs will be more complicated. So this corresponds to joining two nodes of the quiver. This would be the NF equals to 3. And then you can go on until local P1 times P1. And you see that the process fails for reasons that we can discuss separately if you try to go down to local P2 that has no gauge theory phase. So I will not talk about this final part. So maybe I'll just conclude here. If you want to hear something about the relation to WKB approximation, we can talk about it in separately. So I'll leave with the slides on open question if you want to give a look. Or I don't know, if I have 2 extra minutes, I can quickly comment, but this is all.
So do you want to?
Can I have
2 minutes? Yes.
2 minutes? Well, okay. So this I only discussed SU2 gauge theories. So this corresponds to geometry where you only have one compact 4 cycle. So there's only one fundamentally magnetically charged state in this description. But of course, you can do the same for higher rank gauge theories. These are so-called YPQ geometries. And in fact, for these YN0 geometries, you also find you have, in that case, for SUN super YAMLs, you have a ZN symmetry. And you have this algebraic solution also in that case. The only question is, so the algebraic solution holds on general grounds. But what it's problematic to find is this to compute the states that are on this limiting ray. So now it seems that the symmetries of the theories are not enough to obtain also the states on the limiting ray as it was done for the SU2 case. So for that, you do have some amount of information, but not a complete one, at least for now. And there's a bit of a puzzle because if you think about how these cluster variables enter in 4-dimensional gauge theories, well, in this case, they're the so-called Fokon-Cherev coordinates, which we partially saw this morning, at least in the questions, that parameterize the monodromies of these Schrödinger equations that appear in class S theories. And but here, so their monodromy is in WKB approximation. But here instead, we do have this description in terms of monodromies, but at these special points. So one needs to see if this Cupan-Levé, which is a bit weird statement because they're highly, from the point of view of the integrable system, they depend on time. Instead, the monodromies in 4D, they're independent of time. So you have this bit of a clash between what you expect in 4D and what you see in 5D about the time dependence. And this might lead, and this is something that we're working about, at some more geometric approach to QWKB that we're working with Pietro along the lines of what is done for the differential case. And finally, one question that I think it's probably one very interesting one is in 4D you have these tau functions which are non-perturbative partition functions. Now for these 5 theories, actually you can define these tau functions from the equations that they satisfy, but a good definition, geometric definition of these tau functions, that is the one that would lead you to these Fredholm determinant formulae and non-perturbative approach to this partition function is kind of still lacking in the 5D setting. So a very nice open question for this 5D setting is, what is a good non-perturbative partition function in 5D, starting from just geometrically? Yeah, so these, I think, are good open questions to think about, and thank you for your attention.
Thank you for the nice talk. Are there any questions?
By this non-perturbative partition function, we do not mean Nekrasov function.
So I mean more something like a Fredholm determinant formulae for general monodromy data. So of course you have this TSST correspondence. You have some Fredholm determinant that usually correspond to one parametric solutions, right? But then in the general case, so essentially what I would like is a definition of the tau function, like the logarithm in the 4D cases, the logarithmic derivative of the tau function is the Hamiltonian. Instead, in 5D, you have the bilinear equation. That's perfectly fine. But it's, at least for, I don't find it very intrinsic. It's not stemming directly from the geometry of the Calabi-Yau. And then if you have a Fredholm determinant formula, then the studying different expansions around different points in modular space, it's much more feasible than if you just have just the instanton expansion.
But Nekrasov partition function actually is convergent. It's not a symptotic expansion. Can you prove that it's, I mean, it's summable?
Well, it is convergent, but for example, if you expand it around, let's say that you're doing SU2 super Yang-Mills, if you do a long distance or short distance expansion, you would need to use very different coordinates in the Coulomb branch. And the actual Nekrasov, if you expand it around t equals to infinity, lambda equals to infinity, then the actual Nekrasov functions, the combinatorial factors, they're very different and very complicated. But this is something that with this Fredholm determinant formula is just you expand this Fredholm determinant, which is an analytic object, around a different critical point.
Which Fredholm determinant do you mean? I think it works only for this TSST Fredholm determinant, and for usual and the usual and kind of general Fredholm determinant is more or less the same as recent Nekrasov functions.
Well,
it does not help much to go to some other point.
No, but for example, as you know very well, what you can study are, for example, the factors between the expansion around the different critical points, and that you can study in just with this Widom constant approach. It's much more feasible than with the TSST correspondence, and that has a meaning in terms of generating function of this transformation for the coordinates on the Coulomb branch. And this allows you to patch your partition function across the moduli space.
Any other questions?
I was a bit confused about this algebraic solution. The differential essays, algebraic solution corresponds to tiny orbits of group in the character, right? These orbits can be actually very big, even arbitrarily big, whereas in your case I have the impression that orbits like size 1 or size 2.
Well, or this is
a completely different story.
what I found is, like, for example, in these cases, you can have larger involution. So, for example, one part that I didn't discuss was for Cupan-Levi 1. So SU2 and F equals to 2. There is another involution that you can study, which is a Z3. And as I said, for example, for SUN, it's Zn. So the orbit can be as large as you want. But even for these rank 1 cases, for Cupan-Levi 3, you can study, for example, a Z3. But then you see that you have this problem of what I call the wall of marginal stability. So there are other algebraic solutions, but they don't seem very meaningful for this, or at least in a straightforward manner. For example, what happens for this Z3 case is that so the algebraic solution is like on a wall of marginal stability, it's physical, but then you can deform it a little bit, and then you do find you're still within what I call the collimation chamber, but you start seeing wild higher spin states on this accumulation rate. But the problem is that you thought that, okay, I deformed, I think I went away from this wall of marginal stability, but then you check what states lie on the limiting ray, and they are mutually non-local. So you're kind of, in a hidden way, you're still on a wall of marginal stability. So it's not a one-to-one correspondence between what is an algebraic solution on the integrable system and what is a physically meaningful solution of these thermodynamic Bethe-Ansatz equations. So yeah, I guess that's.
Okay. I assume there are no further questions, so let's thank Fabrizio again. So we have